In the last part of section 5.3, I want to introduce another type of growth model. It's called DLA, diffusion limited aggregation. From the name, you can see that the purpose here is to produce aggregation through diffusion. But this is not a free diffusion. It is a diffusion with some limitations. So it's called diffusion limited aggregation. Okay. Let's say how to add limitations to diffusion. Okay. Let's just talk about its advantages first, because that's the reason why people designed this type of diffusion model to simulate aggregation in 1980s. Okay. Firstly, it has very simple algorithms. Okay, and then good at reproducing many real-world objects, cities, the expansion, growing of cities, and fire propagation, and etc. And maybe the the expanding of bacteria colonies. Right, later you will say, and in triggering analytical complexity despite its simplicity. So the algorithm itself is very simple. We'll see later, but it can produce very complex and interesting aggregation spatial pattern, which means that a lot of people can do analysis on it and try and use it and apply it to different real world phenomena, right? So again, it's a very famous and classic and useful building block model, okay? So what's the algorithm? Well, what are the steps? Okay, first step, we put a seed in the middle, on the middle of the lattice. Okay, seed a single occupied site. So after first step, only one site is occupied on this lattice. It's the seed on the in the center of the lattice. Okay, and then we release a random walker a long way from any occupied site. After the first step, it means that we release a random walker far away from the seed, right? And let it wander. Of course, you can assign different rules to this walker to let it wander. It could be a basic random walk, simple random walk, or any other a random walk policy or rules. You can apply any random walk rules to this walker. It will walk, it will wander, right? Until it is an unoccupied site. Until it is in an unoccupied site, neighboring an occupied site. When it stops and occupies that site, and we repeat this process. It means that when you assign a seed to the lattice, and you start to let this walker wander, it will continue to wander until it touches that seed in the center of the lattice, and it will disappear. It will occupy that a site neighboring the seed and then disappear. And then you release another random walker to repeat the same process, but this time is this walker has higher probability to occupy a site, because now there is the seed itself and another site occupied by the last walker. So now there are two sites occupied on this lattice. So it's easier for this second random walker to occupy a site. And we repeat this process, right? We repeat this process. This is DRA. It's simple enough, right? So you will say that the aggregation, the spatial pattern, this aggregation is not simply the result of the diffusion of the seed. Actually, the seed at the very beginning does not move. Who creates this aggregation in the end? It's all those walkers. Okay, so it means that the spatial pattern, the trajectory of these walkers, these trajectories, these movements of these walkers, they decide the diffusion process. Not only the seed itself. Okay, the seed itself is important because it is the starting point of the diffusion. So where is the limitation here? Why is it a limited diffusion? Because there is randomness in each walker's trajectory, in each walker's movement. That's the limitation, okay? The collisions of many sticky random walkers builds an aggregation structure, okay? And this process can be carried out, can be simulated on lattice, restricted to lattice locations and adjacent neighbors, or off lattice continuous space with distance radius defining adjacent, okay? If we're talking about DRA in continuous space, of course, there is no cells, there is no sites. So how can you define neighboring? How can you define if a walker has touched that seed or an occupied site? You can use a threshold of distance to do that. If a walker is close enough to an occupied site, then we say now this walker can occupy the current location and rest. So the next walker will be produced and repeat this process. Okay, so in this course, we're only going to talk about to discuss the situation for unlattice DRA. Okay, so the DRA itself is simple. The algorithm is simple, but it's computationally expensive. Why? Because you have to release this random walker every time and let it wander. And since it is very far away, of course, we can define how far is far away. That's another story. But when you release it, it will randomly, let's just assume we'll just use simple random walk rules for this walker. It will literally random walk across the space until it touches the seed. So you actually don't know how long will it take. So back in 1970s or even 60s, when computers were not that strong, were not that cheap, so people didn't have the resources to implement this model. So DRA is actually computationally expensive. Today, for our daily PCs, it's not a problem anymore, okay? And a heuristic is a shortcut to save computing time, which means that we want to add some variations into this model to make it simpler for computers, easier for computers to carry out, okay? Okay, but the results are still similar. We still want to form an aggregation using the framework of DRA, using the general idea of DRA. How to do that? We can change the start radius, release the walkers just outside the cluster radius. Okay, I will show you examples later, but now let's just read through these rules, okay? Some variations to speed up DRA. And we also can have a return radius. If the walker wanders more than a set distance from the original cell, return it to a point on the circle from where it originated. Okay, because distance wandering involves computational effort that has no effect on the growth process. Like I said, since this walker is wandering randomly, it could just go further and further away from the seed because it's random, right? So let's just give it a threshold of distance. If the distance between the seed and the walker is just too far away, it's just beyond your threshold, let's just drag this walker back to its original point and let it wander again. So we can save some time, we can save some computational power for the PC, okay? Let me show you a DRA model. It's model 5.16, and this is a model. Let me make it larger so it's easier to observe, okay? So here we have several things on this lattice. Firstly, there is a white cell in the center of the lattice. So you can guess, obviously, this is a seed. Okay, so this white cell here is the only occupied cell on this lattice. We also have a circle with what? With gray cells. It's a circle with a fixed radius, right? So when we're using this policy for worker, fixed circle, each worker will be released on a specific or randomly selected site on this circle, and it will wander maybe far away from the seed, maybe towards the seed. But when that worker touches the seed, it will occupy that neighboring cell of the seed and disappear. So another worker can be released somewhere on this circle and do the same thing and repeat the same thing. Okay, and you can change the policy here or a method, starts method here. We can use something called advancing circle, which means that the workers, they will not be released on this circle. It will be released somewhere away from the current cluster. And this somewhere is a distance, is a location randomly selected, but this location should be away from this seed with a specific distance, and you can change the distance here, okay? And the return radius, this is what we talked about. This is a threshold of distance. When the walker is wandering just too far away from the seed, the distance between the seed and the walker is just above the threshold, that walker will be reset. Okay, go back to your origin point and start wandering again. Okay, so now let's just try to use fixed circle first. Set up. So when we're talking about fixed circles, these two parameters, they do not work. Okay, so go. So you can say a lot of sides on this circle, they are currently red. Each red side is a starting point of a worker. And let me stop a little bit. Let me repeat this, okay? So we have 1, 2, 3, 4. We should have 15 red sides on this circle. And when the first worker touched the central cell, right, and occupied the neighbor of the cell. When this worker touched that seed, right, and this cluster is becoming larger and larger because more and more workers, they arrived at a specific site neighboring this cluster and occupy that. So the cluster is increasing, right? So if we let it go, you can say that a tree structure is actually forming here, right? We have a lot of branches, and this tree here has another name. It's called Brownian tree, because this tree is formed by Brownian motion or Brownian movement. Whose Brownian motion? All those workers. Okay, okay, and we can color by time. So you can say red areas, they are indicating cells that were occupied at the very beginning of this simulation, then yellow area, then blue area or blue sites. All those blue sites, they were just occupied recently. If we let it go, we say that this Brownian tree is still increasing, it's still growing, right? We can color again. Okay. So if we change this strategy from fixed circle to advancing circle, and we start radius now is let's make it very big, 20. Okay, and when the worker is very far away from the seed, it will be dragged back. Okay, let's just use max value and set up and go. So you can say now there is no red sets on this circle because this circle doesn't work anymore. Instead of that, you can say there are right sides surrounding this cluster, right? Because after each each occupying, another worker will be released 20 units away from the cluster, from the outer boundary of the cluster, and work again. Okay, if we continue to let it run, you can see that more and more new workers they're released around the cluster, and they are trying to touch the cluster and occupy and die. So another worker can be released. Okay, so yeah, so you can say that some workers they are now some dead workers, right? So you can say all those sites very close to this current cluster, they used to be starting points of workers, right? But now they're actually touching this cluster. But they are the past, right? New workers, they are always produced 20 units away from the current front of the cluster. Since the cluster is increasing, okay, you can say more workers, they are assigned to a location, to a random location, 20 units away from the cluster. Okay, so yeah. And you can also notice that all those starting points of workers, they cannot be occupied anymore. Okay, of course, you can say that, okay, they can still be occupied, but you can read the code. The code here says that, okay, if a site has been used as a starting point of a worker before, then it should not be occupied. Okay, it's all about programming. Okay, color by time. Yeah. So this is diffusion limited aggregation. There is diffusion, but it's limited by the random walk of all those workers. Because when a worker touches the seed, then maybe next worker touches the cluster, then there is a new occupied site. So the aggregation increases, so the aggregation grows. So this diffusion is limited by the movement of workers. Okay, let me get back. Okay, start radius, that this is start radius, and we also have a return radius, right? You can use this return radius slider to control that, right? Of course, if you change the strategy to fix the circle, these two parameters, they do not work, because all the workers, they will be released on this fixed circle. Okay, let me get back here. Yeah. So DRA properties. Firstly, path dependence. Of course, the path, the trajectory of a worker matters. Okay, system growth in the future is strongly constrained by what has gone on in the past, right? Similar to Eden growth process, right? The growth of the cluster depends on the movement, the random movement of the worker. You do not know where this worker will go, and you do not know which neighbor of the current, which neighboring cell of the current cluster will be occupied by the next worker. So you don't know that, but the position of new occupied cell matters because it will make the cluster larger, and so it affects the occupying the occupying behavior of the next worker, right? So the history always matters, and we as a result of DRA, we have this Brownian tree. Okay, and this tree itself is a fractal. Still remember fractal shapes? They are scale irrelevant. They are scale irrelevant shapes, which means that the spatial pattern of them doesn't change no matter how you change the scale. No matter how you zoom in, how you zoom out, you will always see this convoluted spatial pattern. Okay, okay. So the DRA pattern is fractal object or fractal shape. It's a detailed, recursive, and indefinitely self-similar mathematical set. Okay, so now we have 6 figures showing the process of a DRA, a simulation of DRA. This is the pattern at 2,000 steps. This is a pattern at more than 32,000 steps. But you can the pattern of this tree does not change during this process. So this is A, this is F, right? So you can totally consider F is the zooming in of A. Consider we have A right now. If we zoom it dramatically, you will probably have a spatial pattern like F. But A and F, they're actually 2 patterns at different steps. So this is fractal shape. No matter how you change the scale, how you zoom in, how you zoom out, the spatial pattern stays the same. So it's scale irrelevant. Okay, for this specific DRA pattern, it has a fractal dimension of 1.7 in the 2D plane. So you would ask, how is a dimension a decimal? Usually we say one-dimensional, two-dimensional, three-dimensional. It's always an integer. How is it possible to have a 1.7 value for dimension? That's the interesting part about fractal objects. The fractal is a branch, the fractal analysis of fractal is a branch of mathematics. I'm not an expert in mathematics, but the interesting part about fractal analysis is that in this realm, dimension can be something other than integers. Okay, so we use these decimals, for example, 1.7, to describe, to address the complexity of the fractal shape you are looking at, you are interested in. Okay, so this is good enough for this course, but if you're interested in fractal shapes or the mathematical theories of fractal shapes, you may learn more from the internet, from other places. But now you should know that what you need to know here is that the spatial pattern produced by DRA is a fractal object. It has a dimension of 1.7 and it's scale irrelevant. No matter how you change the scale, how you zoom in, how you zoom out, you will always see this spatial pattern. Okay, it's like a nerve system in your brain. It's always like a bacteria, a colony. Okay, or it looks like a watershed. There are mainstreams, there are branches. So as long as you can apply this pattern to a real world phenomenon, you can use the DRA model. You can use a DRA model to simulate it. Okay, and DRA is also anomalous diffusion. It's not faster than normal diffusion, it's slower than normal diffusion, or it's slower than the easy linear diffusion. Okay, so this is DRA I want to introduce. And in the next video, I'm planning to finish the last part of chapter 5, chapter 5.4. We're going to apply the framework, the percolation and growth framework to different realms. Okay, thank you.